Andy, you're good to go.
Excellent. Thank you, Megan. Well, welcome to today's webinar, Metrics That Matter, Evaluating Green Stormwater Infrastructure Performance. I think I'm going to just give it looks like people are still joining at a good clip here. I'm going to give it another few seconds and then we'll jump right in. As we get ready to start the webinar, I wanted to thank the Southwestern Pennsylvania Commission and the Water Resource Center for hosting this webinar. They are currently planning future workshops and webinar topics, so please reach out to Erin Keppel-Adams. Her email's on the cover slide here, and let her know what your needs are. She's happy to try and accommodate your requests, and I think she does a great job at that. So thank you, Erin. Okay, it just hit 12:01, so I think we should dive in. There's a lot to cover today. I did want to mention that a PDH is available if you attend the full webcast, and that is posted under the handout section of the GoToWebinar here. And I'm Andrew Potts. I'm with Jacobs out of our Philadelphia office. Been working on green stormwater infrastructure projects for over 20 years. So really excited to share some of that along with my colleagues, Dan and Annie. Dan's out of our Philadelphia office and also has a very long history with green stormwater infrastructure projects. And Annie has been out inspecting sites all through the region and is going to share some of the insights that she's seen over the last few months in that endeavor. And Tim Prevost, the Alcosan manager of wet weather programs. This webinar was actually one of his ideas, and he presented some of this material at last year's Three Rivers Wet Weather Conference. So some of you may have seen some of it there. We've kind of expanded and updated quite a bit of that, and hopefully he'll be joining us for the Q&A session. So without further ado, let's jump right in. See if the controls are working here. There we go. Excellent. Agenda. Pretty high level agenda here. We'll just quickly talk about the objective and then kind of walk through the various stages of implementation and how you can think about the metrics that matter during those stages. So from planning, design, construction, into post-construction, and even operations and maintenance. And then we'll finish up with some conclusions. But before we get too far, we're going to launch the first poll. Some of you may have seen this or a similar question in a previous webinar with SPC, but we like to just gauge the audience and understand how much experience you have and where your interests are. So please take us a moment here and choose the choice that's most appropriate for you and your municipality. Give it 30 seconds or so. All right, let's go ahead and close the poll in 5 seconds. Good. All right, so excellent. A lot of the audience here has already implemented some type of GSI. We do have quite a few that are considering it. So great. Hopefully this will help you inform your decision. And then a tie between yes, we're planning to, and no, not unless we have to. So great background. Thanks for giving us your feedback there. Starting off with our objective, just quickly paraphrase this. Obviously, with all the work associated and reporting requirements associated with the MS4 and COAs, we're hoping this presentation will share some of the methods of assessing different types of GSI projects. From site analysis all the way through post-construction and operations and maintenance, these methodologies can provide reasonable estimates and assurance, hopefully, of project performance. There we go, got control back. Planning approach, starting with the planning approach. What type of information is important to have when you think about the scale and the potential benefits and the type of GSI you might apply? Well, lots of different categories. There's obviously a lot of information about the site you need to gather, the typical things, subsurface conditions, soils, utilities, etc. Existing drainage conditions. What's your stormwater network like? Do you have flooding issues? Do you have water quality issues? What are your overflow volumes in this area if you're in a combined sewer system? What is the potential drainage area that you could capture, and what are its characteristics? And this is important, as I'll just jump to the next slide, because it really demonstrates you really need to think about what's going to be coming into your practice. So you're assessing the expecting runoff volumes, the sediment, the trash, debris. Those characteristics can help you decide what type might be appropriate, also what pretreatment needs might be required, and then also what O&M should be expected. So those are all critical things as you're making these decisions. Data sources include GIS. A lot of the baseline information is freely available in GIS for the region. And then, of course, you're going to need to typically supplement that with survey and other field work, geotechnical investigations, potentially some stormwater sampling and pre-construction monitoring where that's also appropriate. How do you gather the information? Well, as I said, a lot of it's available on GIS, and actually Alcasan, with their Controlling the Source report from 2020, assembled a lot of this information and synthesized it in a web map for their combined sewer area. So if you're within that area, you can go to the link here on this page and it will take you to the web map, and you can look where there's opportunities and constraints layers. Here's an example from Kennedy Park in Sharpsburg. You can see relatively low constraints. And so this was identified as a potential GSI location. And that information was then used to develop a concept as shown here. And I'm gonna get more into this in a few slides, but this really set the stage, the foundation, if you will, for starting to estimate what the potential benefits could be. Often one of the first things you have to look at is what type of practices might be most appropriate. We've already talked about some of the factors that go into that in terms of drainage characteristics. There's also this useful information. These are some figures out of WEF's Green Infrastructure Implementation Manual that we helped prepare a few years ago. And it just walks through the different layers of factors that go into choosing a BMP. So there's kind of regional watershed scale factors. There's physical feasibility factors in terms of what the site can support. There's land use and site issues. We've already talked about some of those. And then there's a whole range of potential community and environmental factors that might come into play, things like aesthetics and safety and visibility. So we kind of look at the nexus of all those, and you get to those optimal GI practice types that will be appropriate. And then you, of course, have to layer on the economic considerations. So it's kind of an iterative process to choosing those most appropriate practices. In terms of what the practices are, these videos from Gwinnett County are, I think, really great in showing how the practices function and kind of their basic construction and materials. So you can see here by retention cell, the various layers and key materials, and then how they actually start to function in a rainfall event to provide those benefits that we're trying to estimate and confirm. Share. There are videos available for 9 different practices. I'll just share one other. There we go to the next slide. Here is permeable pavements. And here you can see the various components that are typically involved. under drain system, the stone storage layer, the choker, the smaller stone layer, and then the pavement itself. And as the system fills during a rainfall event, it's performing a number of improvements and reductions to the stormwater flow out of the system. So hopefully that helped just visualize what's happening with some of these practices. So how do we estimate those benefits? Well, there's a lot of options, and it depends a lot on the metrics of interest and also the characteristics of the project and the site. So we're going to talk about kind of 3 levels: least complex moving to most complex, and I'll give an example of each of those. And we should start with the fact that we're looking to, again, what we're trying to estimate is going to factor into what type of methodology. So we could be looking at all types of pollutant removals, or it could be focused more on peak flow and runoff volume, or both of those things. And these figures show how beneficial many of the GSI practices are, and why there's so much interest in them. And you can see they're not only very effective at the flow parameters on the left, but also one of the most effective for pollutant removals like TSS, as shown on the right. Here are some examples. You know, a least complex project might be just 1 or 2 systems, similar designs, kind of smaller drainage areas, simple hydraulics, you know, relatively uniform soil conditions or site conditions. Moderately complex, you're kind of adding maybe a few more practices, drainage areas, maybe you're getting a little bit more larger, and maybe you're having multiple inflow or outflow points and things like that. And then most complex might be a larger site, multiple interconnected practices, more complicated hydraulics, etc. So some kind of examples there. So starting with estimating the benefit kind of in that least complex, probably appropriate for many of our simpler projects. One way is to look at developing a cumulative capture curve based on your precipitation. Here's one for Allegheny County. And you can see for 1.25 inches in this example, catches over 95% of annual rainfall, looking at the long-term rainfall record. And so we can estimate the capture depth for one of our proposed practices. If we apply, assuming we could capture 1.5 inches from a 1 acre area, that 1 acre area receives a little over 1 million gallons of rainfall per year, based on the 37.7 inches of average rainfall. And the runoff volume is about 85% of that. So that's 0.87 million gallons per year. And the capture volume then is 95% of that based on the curve above, which results in little over 0.8 million gallons per year of capture. And when we apply that methodology to that concept for Kennedy Park that I showed earlier, that results in about 2.2 million gallons of estimated runoff capture per year based on the capture depth proposed here and the various GSI footprints and drainage areas as shown. So how does that compare to a little bit more moderately complex example? And here, this is the National Stormwater Calculator, a great tool for looking potentially at these more moderately complex sites. And what's one of the great things about this, you can see it kind of walks you through the various steps as you define your site and your project. And it automatically will import data, things like soils data, topography, weather data. So very useful way to get that type of information very quickly. And then you can select your LID or GSI types, set your sizing parameters, even choose some cost estimating factors if you want to use this for that purposes. And then it will estimate the annual runoff volume with and without the GSI, and you can look at the capture. So for that same example of a 1 acre area with 1.25 inches of capture over 37.7 inches, we get the same rainfall I mentioned before, a little over 1 million gallons. The runoff is very similar to what we predicted with the simple method. Previous example, 0.84 million gallons per year. With the GSI, in this case, we assumed 2 types, rain gardens and permeable pavement. The runoff goes down to 0.07 million gallons per year, so a very significant reduction there based on that 1.5 inch capture. And so the capture volume from that GSI is just under 0.8 million gallons per year. So fairly similar to the simple example. This case, a little bit lower, a little bit, I guess you could say, more conservative. So moving to the most complex would be incorporating GSI into the H&H model. So here for an example for swim. And even in this most complex example, the options range even within this from kind of simple, i.e. let's just reduce impervious in the model to represent GSI, to more complex where you're using storage nodes or the swim LID module to actually explicitly model the GSI. So in this example, we're seeing the input screens for the swim LID module for bioretention. So you can see there's inputs for related to surface on the left, soil in the middle, storage and drain a little bit more to the right than the third column there of input screens. And then there's also different options for actually placing those controls in SWIP. So they could be their own subcatchment, and then you route runoff from a different area onto those, or they can be embedded within a subcatchment. And so there's several different options there as well. So again, it can go, the complexity is quite variable within this technique. And we're not only concerned about flow, of course, or pollutant removal, we're also, a lot of people are taking more and more interest in the triple bottom line. So Dan's going to talk more about how we can estimate those benefits.
Great, thank you, Andy. And thank you all for tuning in. So as Andy mentioned, there's various tools that have been used, lots that we're not going to get into, certainly, and it seems like more and more are coming out every year. There are 2 particular tools that are fairly recent that we thought we'd be remiss if we did not get into a little bit. And the first tool, as Andy alluded to, is the Water Research Foundation, the WRF's GSI triple bottom line tool, which just came out, I believe, toward the end of last year. And so this tool was developed in coordination with WRF's Classic tool, which some of you may be familiar with, which is a life cycle analysis tool for stormwater. So it kind of built on that. And again, the purpose is to quantify and monetize the triple bottom line benefits of GSI. So for those not familiar with triple bottom line, of course, that's the financial, social, and environmental benefits. This tool is intended for utility and municipal staff, or really anyone interested in GSI. What's really nice about this tool is that, yes, it does require some expertise and familiarity with GSI, but not with economics. So for someone like myself, who's certainly not an economist by any stretch, this is a very useful tool. And you can see the link in here is where you can get the tool, although I believe you do have to be a member of WRF. If I can advance. There we go. So a little bit more about this tool. It's Excel-based, fairly user-friendly. There are a number of tabs, including a results dashboard, and I'll show you an example of what that looks like. There's key inputs, there's the GSI scenario that can be defined, and then there's tabs for costs and timeline. But I think most of the work that goes into this tool has to do with the 12 benefit categories, and you can see them listed here. They range from avoided infrastructure and replacement costs, energy savings, water supply, air quality. Again, it goes on and on. So it's a very, very comprehensive tool looking at all those triple bottom line benefits. So I'm not going to spend too much more time on this. I do want to walk through very quickly because I think it's interesting the 8 key steps of the framework that is kind of the backbone of this triple bottom line tool, this analysis. So it starts with defining the GSI scenario. So for example, what are the BMP installations? What types of practices, the things like Andy talked about before? How many acres are managed? What's the volume reduction? The next step is establishing a baseline. So what is the gray infrastructure alternative that we're going to compare against? The next step is identifying the full range of benefits and costs. And obviously this is going to vary depending on your community, your region, and the types of GSI that's being implemented. So continuing down the list, probably the most important, maybe not most important step, but probably the step with the most analysis involved is the screening of benefits and costs for the appropriate analysis approach. So this involves analyzing the benefits and the costs. So it's quantifying the benefits in physical units, for example, the energy savings and associated reductions in emissions, and then valuing the physical benefit units. In other words, this is monetizing, things like avoided healthcare costs. Another step in this is identifying and estimating life cycle costs. So looking at the capital and establishment costs, the cost to purchase land, for example, financing, maintenance. And then there are other things that may not be easily quantifiable, so need to be qualitatively described. So the tool allows for that as well. The next step after that's done is to conduct a sensitivity analysis on the key values. You really, in this case, you're trying to find out what's driving your results. And then you're summarizing and comparing all the benefits and costs. This would be the net present value, the annualized benefits, et cetera, et cetera. Second to last step is here is understanding the key emissions, the biases, the uncertainties, and then finally communicating and replying the results. So we can see here an example, and I should mention too, there is a fairly detailed report that was issued at the same time as this tool, and it has a number of case studies, including Lancaster, Pennsylvania. And here we can see an example of the output from this tool for Lancaster, showing the present value benefits. And you can see, for example, the financial benefits were 53% of the total. So the second tool that I wanted to bring up and discuss briefly, at least, is a continuous simulation modeling with infiltration tool that came out last year. It was a product of the Green Infrastructure Leadership Exchange, the GILE, and it was led by the City of Kitchener, Ontario, with support from Lotus Water and Jacobs Engineering. A number of cities in North America participated in this, so there was kind of a good regional or a good cross-section of North America in different regions, different rainfall patterns. And the purpose here was to create a tool for non-modelers to be able to predict the volume capture and water quality benefits of different GSI scenarios. It's a fairly simple and straightforward tool to use. You can see on the right, it simply involves, again, it's spreadsheet Excel based. It simply involves entering information in, not a whole lot of information, and then getting results. And the link is here. I believe I think the Kitchener spreadsheet is available to the public. I don't believe all the other cities' tools are available at this time. So a little bit more about this tool. Again, the backbone here, this is essentially a sophisticated lookup tool. And the backbone is literally hundreds of continuous simulation runs that were done in SWIM. So the modelers looked at a number of variables, the GSI type, whether or not there was an underdrain, what the sizing factor would be. That was another way of saying loading ratio. So in other words, how much drainage area is draining to a certain sized GSI facility. And then the soil infiltration rate. So all those different variables went into, again, hundreds of different model runs. And the BMP, the GSI types, I should say, that were modeled are the more common ones. So bioretention, green roofs, infiltration trenches, and permeable pavements. And these were modeled with very kind of standard dimensions. The tool is set up for use with 2 GSI practices. So for sites that might have multiple, you would have to use multiple versions of this tool and kind of combine the results separately. And what this does, as I mentioned before, you input all the information, your GSI type, your area, the infiltration rate, and the result is your annual runoff reduction as a percentage, and then or your annual water quality treatment as a percentage. So the benefit here, as we see it, is an easy to use tool that yields right-sized GSI for your site based on a lot of modeling that was previously completed by others. We see tools like this really becoming more and more common, especially as communities move away from design storms, so the synthetic 24-hour design storm, and instead focus on the long-term rainfall data. One possible beneficial outcome of this tool could be a smaller but just as effective GSI system. So in other words, it's a system that's designed for real or possibly even projected rainfall, but not necessarily some of the kind of oversized or over-designed systems that event-based sizing methodologies might yield. Whoops, I think we went a little too far. We have our second poll question here. And just to kind of take a break and think about what you've heard so far, we thought it'd be good to ask, how do you typically estimate the potential benefits and performance of your GSI projects? Is it a formula, a spreadsheet? Is it something more moderately complex, like Andy mentioned, most complex, other, or we don't typically estimate the benefits? So we'll give everyone a few seconds here to put their answers in. All right, hopefully that's enough time for everyone. We can see the results. So it looks like the majority use a formula or a spreadsheet type approach to estimate the benefits of GSI. So that's pretty common. I think most GSI projects would be the appropriate mechanism for that. Thank you for your answers. So we're going to continue down the agenda here. We talked about planning, and now we're going to get into design considerations. We're not going to dive too deeply into this. And we should start out by saying, you know, as practitioners of GSI design in the southwestern region of Pennsylvania, we're aware that there are significant challenges to GSI implementation, of course. You know, whether it's the steep slopes, the clay soils, those challenges exist. We think they can be overcome. We've seen them be successfully overcome, and the EPA has put out several guidance documents specifically to address some of these challenges in the region. Yeah, we're not going to get too deep into any of those challenges, but I want to touch on a few other design considerations. And these all do come from the Alcosan Green Stormwater Infrastructure Guidance Manual that came out a few years ago. So we've moved beyond the planning that Andy mentioned, you know, how we go about looking at a site, analyzing the site, where does what type of GSI is most appropriate, where does it fit on the site. Of course, the other thing we need to be considering is, you know, setbacks. We want to make sure we're not too close to things like building foundations or utilities or sewer laterals. So I'm not going to go into detail here, but this information exists. It's good guidance for, again, setting back your GSI to avoid potential issues with some existing features. And then the other thing, of course, is this gets back to right sizing, if you will, the GSI practice. And these are recommendations. These are based on really our experience, the experience of the industry. They're not necessarily hard and fast rules per se, but these are kind of good recommendations for loading ratios. So Again, the loading ratio I mentioned before, sizing factor is another term we've seen. That has to do with the amount of specifically impervious area to the GSI area. We typically see this really broken out by what the function or the mechanism of the GSI is. So is it designed for infiltration, or is it designed as more of a detention system with a slow release mechanism? So that certainly has an impact. For example, here we can see if it's a surface vegetated system that's designed for infiltration, a typical loading ratio range might be 10:1 to say 20:1. However, if it's designed for slow release, we're not as concerned about degrading the infiltration capacity of the soils over time. And so we might allow for 15:1 or even up to 25:1. So a little bit of a higher loading ratio. So a smaller GSI footprint for that same drainage area. And then getting yet even more detailed here, these are some kind of recommendations for actually sizing the GSI systems. Again, all these come from the Alcosan Stormwater or Green Infrastructure Manual. It's a great resource for the region. But here we have two tables. The first is recommended void percentages. These are fairly common, I think, in the industry. Obviously, stone, it has a fairly limited void space for stormwater storage that's commonly used. Of course, there are things like pipes embedded in GSI or even modular storage systems that provide a lot more void ratio. And then the other table here, these are just kind of common or typical storage depths for GSI systems. Went too far there. Sorry, I'm seeing a blank screen. Okay, I'm sorry about that. So another thing to consider during design is how the system is likely to perform after construction. So reduction factors or conservative values for elements that are likely to get impacted during or after construction can be used to improve the likelihood that performance goals are achieved long-term. So some examples of this might be the available porosity in an open graded stone layer, like I was just mentioning before, or the permeability of bioretention and subgrade soils. So some of the factors that go into this might be the type of permeability test that was performed, the variability of the site soils, the level of pre-treatment, the expected sediment load, whether or not we have good control over compaction during construction. There's a lot of judgment that goes into this on the designer's part. How conservative do we need to be to ensure long-term performance? So the EPA SWIM even has a clogging factor for subgrade soils and permeable pavements. So this clogging factor is the ratio of the total volume of runoff it takes to completely clog the bottom over the storage volume of that layer. And this clogging factor can be impacted by the nature of the runoff. So how dirty is this runoff? Again, the amount of pre-treatment provided, the amount and the type, and how concentrated the runoff is to the system. Again, that's the loading ratio. So, and as part of the design, it's also important to keep monitoring in mind so that monitoring can successfully be completed after construction. Monitoring locations need to be provided or at least accessible. And this, of course, is dependent on the project specifics. Different monitoring techniques may be applicable depending on your project. So for example, if it's a small to medium-sized project, then just simple in GSI system water depth monitoring may be all that's needed. Whereas for larger projects, downstream in-sewer monitoring might be optimal to directly evaluate the impact on the sewer system. And maybe this could even be coupled with some, again, in GSI monitoring that can help identify maintenance needs or performance issues in the future. And we'll get into that more later. For projects that are being modeled, the more complex models that Andy talked about, consider how the monitoring results will inform the model and allow for model calibration or validation. So for example, if it's an in-sewer monitoring, making sure that that monitoring location is included in the model. And there's a lot more on monitoring in the Alcosan Grow manual. So here's an example monitoring schematic. And you can see here, this is a permeable pavement project with multiple monitoring wells. And it's at the, and they're kind of out throughout this system and then also at the outlet of the system. And of course, not all 4 of these monitoring wells will need to be monitored at once, but the locations provide a lot of flexibility and redundancy as needed. So we're moving along into the construction phase of GSI. And of course, as we all know, things can change or go wrong during construction, and diligence during this phase can minimize those impacts. So what we see here, this is kind of a list of some of the critical elements that we see that can really lead to a successfully constructed GSI project. So education, educating the contractors. Communication is key. Material test results, lots and lots and appropriate construction oversight and observations. Verifying things like ponding depths and side slopes. These are all critical for GSI. And here are some of the key steps in construction inspection. Typically, we like to see a pre-construction meeting that's separate from a pre-planting meeting. A lot of times planning happens really, really far away or far in the distance from construction kickoff. That planting specific concerns that were brought up maybe at the pre-con meeting might be long forgotten by the contractor. Or the planning crew might not have even been at that meeting. Make sure that the contractor is using appropriate materials that meet your specifications and that the materials match the submittals. This has been an issue time and time again on many GSI projects that we've seen. Kind of a classic example is aggregate. Maybe the aggregate isn't the correct size or it's dirty. And if it is dirty, it can certainly clog your system and lead to big issues down the road. You want to make sure you check in with the contractor at all critical stages and make sure to inspect before everything gets buried. And once it's in the ground, it's too late to see it, obviously. So conduct a final inspection, including one during a rainstorm, just to see how things are functioning. And then continue to do inspection during the plan establishment period and while everything is still under the contractor's warranty. So again, another plug for the Alcosan manual. There is a full section on construction inspection. It includes a detailed table on inspection guidelines that I'll show you what that looks like in a minute. And detailed checklists, which you can see here. These are examples for infiltration trenches. So again, definitely recommend checking out the manual, and there's a lot more information in there. And as I promised, here's an example of a 3-page construction inspection guidelines table. I know you can't read this, but just wanted to show this, oops, went too far, as an example, really just to demonstrate the format and the content. The 22 construction tasks in the first column correspond to the inspection checklist. And you can see for each task, hopefully you can see, there's a task summary, there's a list of the items that need to be inspected, the timing of those inspections, who's responsible, and then any potential actions that could be done, corrective actions to avoid those problems. And with that, I think I'm turning it back to Andy.
Absolutely, thank you, Dan. So finally, on moving into post-construction before we get to operations and maintenance, just a few quick considerations here. One is to, before you even start thinking about monitoring data, make sure you're looking at your as-built information, doing those weather inspections that Dan mentioned, simulated runoff tests potentially to update your calculations or your model. So photo on the left there is a simulated runoff test. So that might be where you take flow from a hydrant at a controlled rate and look and make sure your system's capturing the appropriate volume, there's not bypass, etc. It's filling as intended. Example of going out in a storm and seeing an apron that's not depressed enough, and so we're seeing a lot of bypass past that trench drain in that example in the middle, and then an inspection of a system at a library filling and performing beautifully as expected. So you're finished construction, and one of the first questions you need to ask are, were there significant changes from your design, from your bid documents? The drainage areas changed, the GSI footprint change, storage volumes, any critical materials, stone, bioretention soils, things like that. Were the subsurface conditions as expected, especially those soils if you're trying to infiltrate? Would that reflect any changes you might need to make? And then moving into monitoring itself, again, think about redundancy to have better confidence in your data and to have backup. So for example, you have multiple depth sensors if you're going with a depth measurement, maybe depth and velocity if you're looking at flow monitoring. So you have some different ways to look at things and QA/QC data as well. See the graph there on the upper right, really great consistent data set there on flow versus velocity, but we don't always see that for sure. Consider whether in GSI or in sewer monitoring or both is optimal depending on your project. Think about coupling. Really like this one, and people don't always, I think, pick up on this. Couple your data with field observations. If you're not seeing what you're expecting, maybe an inlet's clogged, and so the system's not receiving water or something like that. So make sure you're checking that. And then a really cool application of using rain-activated time-lapse cameras to see how the system fills and drains over time. So there's a lot more options these days with remote real-time monitoring and things like that. So consider those. There you can see an example of that time-lapsed photo of a bioretention swale in a parking lot filling up during a rainstorm. And then you're going to use those post-construction monitoring to validate, calibrate your calculations or model as appropriate. Again, different ways to model this in SWIM, and a couple examples shown here. For the sake of time, I want to move into the operations and maintenance after we get through poll question number 3. So which phase of the GSI implementation process have you typically found to be most challenging? Planning, design, construction, or operations and maintenance? We probably should have included funding here, but this is assuming you have the funding. Let's give it another 5 seconds. All right, let's go ahead and close the poll. Interesting. Okay, so quite a few people just the planning. Definitely can be difficulty. No one has any problems with design, which is good. Interesting. Construction, yep, certainly see a fair amount of issues, and then far and away the leader there, the operations and maintenance. So really good feedback, good input. Nothing too surprising there, but let's get into the operations and the maintenance discussion. Megan, can we go back to the slides?
Andy, where do you need to go? I'm sorry.
Back to the slides.
Oh, yes. Sorry.
Excellent.
There you go.
Excellent. And so I will turn it over to Annie to talk about what she's been seeing out in the field on operations and maintenance.
Yeah, thank you, Andy. Yeah, as we can see from the poll result, actually the majority of you would agree that it is one of the most challenging part Let's see the next one. Yeah, but it is also one of the most important part in, maintenance of the GI systems. So therefore, regular monitoring is also important to ensure that the proper maintenance measures are in place and they happen at the right frequency. So from these couple of pictures are just some considerations for maintenance. Well, the one on the left is like a permeable pavement vacuum truck that can be used to eliminate the clogging and any of the particles that get into the permeable pavement. And there's also a mark on the pavement that avoids tampering with the GI system. And also, of course, we have to consider seasonal conditions, especially winter. For example, clearing if you have a permeable pavement that's used for parking or like pedestrian crossing, then it will be important to properly maintain those, such as snow removal and all that. And yeah, on the right, you can see here, we can see like some sediment, soil accumulation around the inlets, but from that, we know that it's working and the flow is going in the right direction, but some maintenance is definitely needed to keep that clean. So this is also from the Auxin Operations and Maintenance Guidance Manual. It provides a pretty good guidance for maintenance plans for GI projects. So basically, their routine, non-routine, and general maintenance activities. And of course, there are different frequencies suggested for different GI types. And the frequencies are also kind of dependent on individual site conditions, which can be investigated further for each individual site. And they also include a maintenance inspections checklist here for, which is important for the long-term performance. So here you can see in the highlighted areas, there are different site conditions that are listed for consideration, and there are 3 categories to each: satisfactory, marginal, unsatisfactory. So basically, these are the guidance or the parameters we use when doing site inspections in the field of the GI systems. And there are, on the column on the right, there are also some suggested corrective actions that could be taken to address these problems. So this is a inspection form that we fill out in the field. You can see there are the site conditions that are listed. This one is for permeable pavement, there's one for bioretention, and of course they have slightly different list of site conditions. But overall, it serves as a guidance of what to look for while we're out in the field. And we also attach pictures to kind of verify or as backup to the notes that the conditions, different conditions we note that we see in the different GI systems. And yeah, so I'm just going to share a few photos of what we typically see in the 15 inspections that was done so far. But firstly, yes, this is an example of an inspection report that will be generated for each site visit. Basically, there's a general project site information, a general description of the site conditions, and basically we list all of the issues or observations that we noticed in the field. And last but not least, some corrective actions that are recommended. And yeah, and on the right, these are the photos we included in the report. Yeah, so far we have done inspections on permeable pavements and bioretention systems. And for permeable pavements, there are, the common issues, just want to point out, there's some clogging, there's sediment buildup, there's some accumulation of debris and trash that we noticed. And very few of them actually have like some settling and crackling that we can see. So, because the pavement is now uneven, there's some of the joints have been enlarged and which definitely needs some maintenance. And these pictures are kind of like illustrates these problems, and we just want to point out that the conditions surrounding the site is also important to take into consideration, because we can see a lot of sediments come from, adjacent areas, whether it's slopes or unstable slopes or some roads that needs maintenance, and there's sediments running off from there. And yeah, another thing that was noticed was the change in drainage areas. For example, these roof leaders you can see have been disconnected, or originally it was planning to collect the runoff from the roofs, but for whatever reason during construction there's been a change, or there has been new development, then they might not be collecting the drainage area they were intended to. So some of these should be taken into consideration too when doing site visits. And actually, there was very few weed problems for the permeable pavements, but there was one here on the right. As you can see, there were weeds growing in the paver joints, which definitely need treatment, and possibly changing up the soil and joint material as well to eliminate weed growth. But yeah, most of them are in good shape. You can see those on the picture on the left, the picture on the bottom. The picture on the bottom, there's actually connected to a bioretention system or infiltration system, which we will go into in this slide. These are just some pictures that illustrates the common issues or observations we find in bioretention systems. For example, on the left, you can see there's a lack of plant or mulch, and of course that changes with the seasons. And for example, like June, actually next month would be a good time to go out and see, investigate some mulch applications or replanting of plants. And you can also see there are erosions, some leaves and debris in the inlet, and sediment buildup around the curb inlets or forebay area. But these are problems that are pretty easy to address. So basically you just need some cleaning for the most part. And these are some that works relatively well. You can see the only thing that's worth noticing was some sediment accumulation, but mostly the plants are growing well, and yeah, in general, the general condition is just it's very in good shape. We can see some compactions in where people walk over the soil, but that's a minor problem, and that can be addressed by putting walking paths, as the picture on the right. Yeah, and with that, to the conclusion.
Thanks, Annie. So just to conclude this, couple key points here. Estimating and verifying the performance of GSI is, of course, critical, and it can be challenging. Fortunately, there's a range of methods available that can be scaled based on the project parameters. Again, the low complexity to most complex that Andy talked about earlier on. And then consider performance at all stages of the project, from the planning stage to the design to construction, monitoring, and then ultimately maintenance, like Annie just mentioned. And I believe that is it. There are a lot of good resources and tools available to assist. The we in this case, I think, is from the perspective of Alcosan. There are a lot of lessons being learned as part of their program and throughout the region. So it should be really useful to the industry to see what comes out of that.
I think it's more the collective way everyone should be sharing and learning from each other. So I think that's the case that we're seeing. Excellent. We have just a few minutes for questions. I see one here came in for you, Annie. What was the most striking thing you've seen in your recent round of inspections?
I think for me, maybe probably not the most striking, but then the most, the thing that I didn't think of before is how much the areas, so you can't, like, we can't just look at the GI system themselves. And I think it's very important to assess the conditions around the systems because they do contribute a lot to some of the issues that might arise in the system. Just like I think some of the pictures that was shown kind of proves that, for example, if the road conditions are deteriorating in the adjacent areas, or there's like slopes that are unstable, so it really contributes to sediment coming in and clogging up the pavements. And I think that's one of the main maintenance that needs to be done for many of the systems. Yeah.
Great. Here's one that came in for Tim, but I don't think he was able to join us. The question is, in general, how is Alcosan finding that the GROW GSI projects have been performing? So I guess I can take that one at a high level, and Tim's contact information is on the screen, so he's always very willing to answer questions about GROW. But in general, I think they're finding that they're performing at or above what was expected typically. So on average, I think there's been an overperformance to a slight degree, but certainly some variability with some performing less well as expected than predicted, and some performing more. So it's been a mix, but overall, I think it's a good story. And finally, I think our last question, Dan, goes to you. What about monitoring for water quality? Is that something that's usually required?
Well, no, I think is the answer. I think presumptive compliance is usually the name of the game there, especially obviously in combined sewer communities. We get outside combined sewer communities, the MS4s, it becomes obviously more of an issue. But it's not something I think that's very common or required in general.
Okay. And one more came in just as I was asking that one. Do you have any example products for the rain-activated time-lapse cameras? Great question.
Yeah, I don't think that's been done at a broad scale. I know there's a project, I believe, in St. Louis. I think that was the example project that Andy showed.
Yeah, so we would have to probably dig on that. And that was a few years ago, so products have probably changed, but we can see if we can find what was used for that example. And I think Aaron did note that the slides will be posted to the SPC WRC website in a few days under the past events page. So we're moved from coming events to past now. And with that, at 12:59, I think we will, 1 o'clock on the dot, we will sign off. Really appreciate everyone joining this and the other series of webinars we've done with SPC, and look forward to additional questions and discussion and sharing information as we move forward.